group and somebody showed you this room, or did everybody individually discover the room by himself or herself? Since we are able to actually find the room, the quantum mechanics is then not a very difficult thing to understand. As you have already learned about what provides, in my opinion, the best way to acclimatize oneself, like best introduction to quantum mechanics, or at least this kind of thing, quantum computation, is by first learning about probabilistic computation, and you know about that, right? You can throw a coin and it can come up head or tail, or as we call them, 0 or 1. What happens, the probabilities of zeros and ones can be represented by vectors, and the stuff that can happen, the procedure which takes a unthrown coin and then describes the different possibilities which may arise as a result of the throwing of the coin, can be represented as a matrix vector or multiplication. You have seen that already, yes? Matrices. And probabilities have to add up to 1, and you know all that stuff. Well, this is almost it, right? Quantum computation is just one step away from that, and it's quite easy to understand if you are already in this probabilistic framework. Some coins are being thrown, and different possibilities of the system are then represented in terms of vectors in which numbers are adding up to 1. Okay, you have had the best introduction. So now let's enter the quantum stuff. The quantum stuff involves some strange discoveries made by several European scientists at the beginning of the 20th century, which really confused them, like for decades, and in fact, like for all the time since then, people are confused really. The way to proceed is to, in my opinion, just like, as they say, bite the bullet and accept that these strange things are there, but they really are correct. All experiments confirm that this is so. So I just have to believe this and then move on with them. So anyway, as far as I can understand, the hydrogen atom has one proton in the middle and one electron around the proton. And I think all of you already know about this stuff about there being several discrete levels that the electron can find itself in. You remember that? Orbitals, I don't know, from high school or early university. The electron can either be in the first level, or in the second level, or in the third level, and I think there are many, many, many levels, but for our purposes it will be okay to consider only the first two, because it is so much easier when you think about systems which have only two different possible states rather than many, many different possible states. Many, many different possible states can be built by bringing together many little systems, each of them having two possible states. So, amazingly, that was the part that amazed and confused them in the beginning, then confusions continued. The electron cannot be in any other place. It is either in level 1 or level 2, and it's not in like level 1 point something. It's not like that. Like jumps maybe under certain conditions from level 1 to level 2 or 3, whatever, but never somewhere in between, intermediate. It's not that thing is not continuous in that sense. It's discrete, as we say in computer science. All right? So only discrete, different possibilities. All right? And that was strangeness number one. But then the really, really strange thing that they discovered corresponds to the following fact about the position, let's say, of the electron. It's both here and here sometimes. It has the possibility of occupying more than one of those levels with different weights at the same time. But when you observe it, when you, I don't know, build an electron level observing device, which reports to you it's currently in level 1 or level 2, right? When you do the observation, you always see it as you would expect in a classical world, in exactly one of those levels, right? It says level something, right? Not a little bit of level this and a little bit of level that. Observations always yield, in that sense, what we may call classical outcomes. Okay? And the probability that you will be observing the electron in this kind of strange configuration in level 1 or level 2 is determined in a strange way. Essentially, I mean, your measurement device acts probabilistically. Okay? It's like here with some probability weight and here with 1 minus that probability weight. So your observations will occur probabilistically. Up to this point, everything is still consistent with what you learned before the break, because, okay, you already know about probabilistic stuff. Something can be in that box with probability 0.3 and the other box with probability 0.7. And when I open them up, I will see it on the right with probability something, and on the left with probability 1 minus something. However, unfortunately, that's not really the case in the case of those quantum things. I mean, it's not the case that it's in one of them, and I don't know which one, but my best theories tell me that the probability that it is in one of them is something, and the probability that it is in the other box is 1 minus something. It's not like that. It's really that it's both in this level with some weight, and in that other level with some other weight at the same time, simultaneously. So if you are accustomed to the notion of a classical particle, as every normal human being is, it's very difficult to accept that something cannot be in the same place, in different places at the same time. All right? However, unfortunately, these things are like that. They are in different places at the same time with different weights, but the weights are distributed so nicely that when you actually do the observation, you will see them with probabilities associated with those weights, and the probabilities of observing them here or here or here or here, and all those probabilities added up together will, of course, add up to 1. All right? Okay. Those weights, the things that I have been calling weights, I am trying to avoid calling them probabilities. They are associated with probabilities. All right? Those weights are called amplitudes in quantum mechanics. Amplitude, as some of you may remember, is a word which is related with waves. If you are interested in waves, that physics course. All right, and there is a reason for that as well. Okay, as you may have heard in many descriptions, lectures, books about quantum mechanics, there is this stuff about saying in quantum mechanics things are like both particles and waves. Things that you normally think of as particles act like waves. things that normally you think of as waves act like particles, and like there is this strange unity, the character of things has got this duality associated with it, they say. All right? Okay, or like one physicist says it, and then the other physicist comes and says, no, that's not quite correct way of saying this, and everybody seems to have a different interpretation about this. Quantum mechanics says, really, although it is, I mean, everybody is quite sure about its formulas, its predictions have been tested again and again with experiments, it's like obviously correct. I mean, the equations, the formulas are correct. People have great trouble interpreting it, understanding exactly what it's like is saying about how those things are doing, really, actually. It's good for making predictions, but for describing the world, the formulas are so strange that everybody, I mean, there are like, I don't know, 5, 10 different ways of interpreting it, and there are like religious factions among physicists. All right? There are the people who say, you know, until you observe it, it acts in a different way, and when you observe it, suddenly it decides on looking like a classical system with probabilities associated with those ways. There are other people who say that the basic formulas of quantum mechanics describe essentially a world with many, many parallel universes acting simultaneously, just like you have in those science fiction movies. And really, in one of the universes, the electron is in level 1, and in the other universe, the electron is in level 2. And the weights that we have been talking about are the weights of the universes, really. Okay? And if I look at the atom and see it in level 1, this means that I have been in that universe from the beginning, right? My copy in that universe, of course, will be seeing the electron in level 1, whereas my copy in the other universe will be seeing the electron in level 2. And like the weights were like were assigned to the universes that we were in. That's one other way of talking about it. The way of interpreting the wave that I have been talking about is like it's a function that assigns really in an indirect way a probability of observing the thing associated with the wave in any location at any position of the universe, which makes everything, especially if you are new to those things, very confusing. And I think really the way physics is taught, at least the way physics, this kind of physics was taught when I was a student, is extremely confusing and alienating, and people are right in thinking that it's not just a very difficult, but also a very, very, very confusing subject. I think we can say this about my talk up to this point as well. But the way you have been introduced, as I was mentioning, to probabilistic vectors, matrices, and ways of thinking about those actions in that mathematical way, I think is a very, very good introduction to quantum mechanics, in particular to quantum computation. So let's, okay, not completely forget about the hydrogen atom and its electrons, but now let's start telling this story from the beginning again, but in terms of those things. Okay, we want to build a bit, something, some physical system which will hold one bit of information. So it will either represent a 0 or a 1, because that's how we build computers, right? And if you are able to build those things, build many, many of them, and have a way of, you know, modifying them in a systematic way by looking, if these two are 0, then this third one should be a 1. So if you are able to do some pretty basic elementary operations on collections of bits, then you are able to build a computer. Really, computers are built like this. And one of the important things that we teach to computer science students is that those levels of computer engineering, like hardware at the bottom and software at the top, are really nicely separated from each other, in the sense that the exact material, the exact technology using which you build the hardware is really not important from the point of view of the guy writing the software. You see what I mean? It essentially means that it really doesn't matter which physical systems you are using in order to build your bits. A bit really is a very abstract thing. It's either this or that, okay? Where you assign meaning 0 and 1 to two different, nicely identifiable states of a physical system, and really which particular kinds of physical systems you use for this purpose is quite up to you. I mean, nowadays it is very, very easy and efficient, and we can fit like millions and millions of bits to a small place using the particular physical systems that we use in order to build those transistors and those chips and so on. But there is nothing which forces us to build our computers from those things. That's so important, right? As long as it can be in one of two states, and you can, like, when necessary, switch from this state to that other state, okay, it can work as a bit. I mean, this can work as a bit, like 1, 0, its position, if I can manipulate and observe them nicely, can work as a bit. Cup full, cup empty, can work as a bit. You can build computers from water pipes and I don't know, any kinds of things, as long as they play the role of like bitness in that sense, they can be used to build computers. All right? So really, these things can also be used to build bits, right? I mean, electron at level 1, let's say that corresponds to bit being 0. Electron at level 2, let's say that corresponds to bit being 1, and forget about the other levels. All right. So by this kind of, like, if I have the ability to manipulate these very small systems, then I can build bits out of them. Nothing strange up to this point. But remember that those have those strange properties. They can be like in more than one state at the same time, if you see what I mean, as I was mentioning, and so on. How will this be useful for my purposes as a person who wants to build computers, if I really am able to use these kinds of things as bits? How will I be representing them in the notation that you have been introduced before the break? Well, I think the notation that you have been introduced before the break is like, there is a vector with 2 rows, and the top row corresponds to the observation probability, or like the probability of the system being in state 0. The bottom row corresponds to state 1, right? And the 2 numbers that you see here have to add up to 1, of course. All right? So essentially we'll be having almost the same kind of thing. However, now, when representing quantum bits, quantum systems which represent this kind of thing, the 2 numbers will correspond not to probabilities directly, but to amplitudes. The weights that I have been talking about, it's in level 1 with this weight, I meant with this amplitude, it's in level 2 with that amplitude. And there is a very easy way of converting the amplitudes to probabilities. I mean, if I tell you that my electron is here with amplitude that and here with amplitude that, it's very easy to calculate the probabilities associated with that. With what probability will I see it in this level can easily be calculated. The only thing that you need to do really is to take the square of the amplitude. The amplitude is a number whose square is the probability that you have been familiarized with before the break. Really, it's the square root of amplitude. Amplitude is the square root of probability. Right? And I am simplifying things a little bit, but from the point of view of quantum computation, it's okay to do that simplification. What I am simplifying is that actually amplitudes can be complex numbers, you know, a plus bi imaginary, but in the world of quantum computation you can understand, I think, everything without going outside real numbers. Really, all you need to do is to allow for negative numbers, which you cannot do in the world of classical probabilities. But since now I am not using probabilities themselves, I am using the square roots of probabilities, it is okay for me to use negative numbers as well. Alright? So I can have a qubit. When you use such a quantum system in order to build a bit, we call it a qubit. I can have a qubit in the following kind of state. Really, any state where the squares of the numbers that you see here add up to 1 is a legitimate state for a qubit or for a more general quantum system. Alright? The square of the numbers should add up to 1. Why? Because the squares correspond to probabilities, and the sum of the different probabilities of observing it here or here or here, the sum of all possibilities should add up to 1, famous rule of probability, that also is valid. You have a question?
Yeah, how about the weight? Weights are not adding up to 1, so
yeah,
where is the rest of the thing?
The amplitudes don't have to add up to 1. The squares of the amplitudes have to add up to 1. That's the thing that physicists tell us. All right? These are not things that you add up, because these are not probabilities.
But like in physical understanding of the electron's position, it's weights, right? But
actually, they never use the word weight, right? I started using the word weight in order to defer using the word amplitude. And the amplitude actually corresponds to, you know, it's a wave, actually, and waves have amplitudes, and waves can be both like this and like this, so the plus and minus really correspond to that. But the probability of observing it corresponds to how deep or how high it is, right? So you map from the amplitude to the probability by taking the square, okay? So really, I mean, if I have prepared my system so that the electron is definitely 100% in level 1, corresponding to state 0, for instance, it would be like this. It would really look very classical in that case, right? With probability 1, I would see 0. With probability 0, I would see 1. All right? But if it's in one of all those other intermediate states are also allowed, as long as the square of all the amplitudes is 1, square of all the amplitudes are adding up to 1, it's okay. It's a legitimate quantum system. It really can, I mean, you really can manipulate something so that it's like that, right? And then later somebody may come and observe, and he will see the actual classical values with the associated probabilities as a result of that observation. Nothing mysterious. Or maybe mysterious, but I mean, there is nothing wrong in it. accepting this. Because if you don't accept this, there is no way of going forward, right? The first lecture of a quantum computation course involves saying this a lot, right? Okay, I know this is not very intuitive, but you have to accept it. I mean, it's really correct. The physicists assure us that it is correct. Okay, so this, or maybe this, all those are legal possibilities for describing the state of a qubit. All right? What's the probability that I will see 1 when I observe this? Square of minus 1 over root 2, 1 over 2. Oh, it's 1 over 2. All right? Okay. So observing, for instance, qubit in this particular state really is something like throwing a good coin, because you observe 0 or 1 with equal probabilities at the end. Okay? One way of thinking about quantum states is they are coins, really. Okay? You have a question?
What's the difference between the states with minus and without minus if they have the same probability?
Yeah, they correspond to this and this in terms of the wave, where like no wave corresponds to the line in the middle. From our point of view, from the observation probability point of view, there is no difference, right? So qubit at this state and qubit at that state, by observing it, you would not be able to distinguish between them, right? Okay. All right. There are lots of things in the quantum world that we can't see, we can't distinguish by our observation devices, or that can't be distinguished from our kind of world, I should say. Are we okay? Okay. So, yeah, that's how a quantum bit looks like. In what way is this leading to interesting situations? In what way is this like important for people like me who are not physicists but interested in computation or the transmission of information and so on? Well, the following kind of thing can happen. You, for instance, have already seen that 2 bits side by side, if you look at them as a single system, is actually a bigger system with 4 possible states, right? You have already seen this, right? 2 bits side by side, 0, 0, 0, 1, 1, 0, all right? So like 1, 2, 3, 4 positions now in that vector, so on. And I can do something like that by putting 2 qubits side by side, all right? And really then, that 4-state system corresponding to these 2 qubits has a vector describing its state according to the same principles that I just mentioned. I mean, the only thing that nature really cares about is that the squares of these 4 numbers should add up to 1. In particular, it may be in such a state. Remember, this row corresponds to 0, 0, this row corresponds to 0, 1, 1, 0, 1, 1. All right? Okay. A 2-qubit system can be manipulated to be in this state. Are you all okay? There are also, you may have seen physicists using things like this. Or even worse, some strange Greek letters here, right? This just means, I was really amazed when I learned that it means such a simple thing. So This means this vector. My qubit is in state 1. That's it. Definitely. They seem to like this notation. Alright? If you memorize this notation, then you can write complicated vectors in formulas like this. For instance, my first qubit example can be written like 1 over root 2 qubit 0, 1 over root 2 qubit 1. Do you see this? Once you see things like that, never worry, they are just vectors. Alright? Aha, so this one corresponds to 1 over root 2 bigger system at state 0, 0, 1 over root 2 bigger system at state 1, 1. Yeah? When I look at my 2-qubit system, I will observe either 0, 0 or 1, 1 with equal probability. Seems okay until now. Okay. By the way, you may be wondering about how we can obtain these. So, you have already a CNAT here, right?
Yes.
Okay. So my talk will end in 10 minutes. So this CNAT thing is very useful, as you see. It's an operator that you can execute on 2 bits, and it can change the combined state of the 2 bits depending on whether the first bit is 0 or not. You are familiar with this now. In order to represent elementary quantum computational operations, things that we may do on qubits or collections of qubits, we also use matrices. This entire seeing computation as essentially multiplying vectors representing the possible states of our computer with matrices idea is beautiful because it can be supported to understand about quantum computation immediately. I mean, quantum computation is the same thing, right? I have a computer whose state can be represented as some vector, as we have all agreed, and the thing that the computer is doing, the computation, the changes that it is doing in its in the bits in its memory, can be viewed as multiplying that vector with an appropriately prepared matrix. So in that sense, programming is really matrix engineering. It's just like, which matrix is like the best matrix to take the initial state of my computer and convert it to some other vector, which then people can observe and see the solution. All right? Really, programming is can be seen in this view as preparing good matrices. If you are a good programmer, you prepare wonderful matrices and so on. So in the world of quantum physics, the laws that those people discovered in the beginning of the 20th century also tell something about some syntactical rules that matrices should obey. If you are a quantum program, then the matrix associated with the transformation that you are doing on your memory has to obey some rules. What were the rules in the world of classical probabilistic matrices? The rows, or no, the columns should add up to 1, right? Because probabilities, when you add them up, 1. Can you guess what the rules for quantum matrices is? Yeah, the sum of the squares of the columns should add up to 1. But not just that. That plus the sum of the squares of the rows should also add up to 1. And by the way, if these two happen, the following thing also happens. take any two columns, and their, what do we call this again, dot product? Yeah, in the world of, since I'm only using real numbers today, the dot product of these two vectors, I mean multiply this and that, multiply this and that, multiply this and that, and then add all of them up, should be equal to 0 for all different pairs of columns that you see in your matrix. That's what the physicists are saying. Only matrices like that are legitimate quantum programs. Anything, any matrix which doesn't do that, it can really not be implemented in the real world. Right? Okay. Using an amount of memory which is equal exactly to that. Because those rules only apply to closed systems and so on, but it's quite difficult to learn in this way. All right. So, for instance, amazingly, the CNOT gate, the CNOT operation that can be done on two bits, as you see, is a very valid quantum operation as well, because its columns obey everything that I just mentioned. Right? So it really can be used without any like quantumization modifications or anything in a quantum program as well, because it's a legitimate quantum operation. So one elementary thing that you can do in your quantum operations is take two qubits and CNOT them. Another famous quantum operation is this one. Check that it is really a valid quantum operation because it does everything that I said. Right? If this was not a minus, then it wouldn't be doing that because the dot product of these two things wouldn't be 0. Okay. So this matrix is associated by this very famous French mathematician. So it's called, since French people in this case don't read H and D, the correct way of pronouncing it is Hadamard. Right? But everybody, of course, calls it Hadamard. Okay, so this H operation really looks like a coin throwing operation. Did you have something equivalent to that? Yeah. Normal coin throwing corresponds to, I think, 1/2s all over the place. Whoop, coin throwing. This is quantum coin throwing. I mean, if I originally have a bit in pure state 0, boom, applying Hadamard to it gives me my bit in this state, and then when I observe it with wonderfully equal probabilities, I will see 0 or 1. All right. So the nice thing, I mean, why did we mention Hadamard and CNOT right now? So Hadamard plus CNOT are so good that using them you can write really any quantum program that you like. Any of those things that you will be learning in these days, and really any other quantum idea that somebody can have for quantum computation. Okay? You can approximate any big quantum matrix using combinations of these two guys applied on different qubits, one after another, in a reasonable way. Do you see what I mean by approximate? I mean, applying that quantum matrix or the combination of Hadamards and CNOTs would give you almost the same observation probabilities at the end. Right? So this is very good because normally in computation we want elementary gates. Really, I told you that programming is matrix engineering, but engineering a matrix which is like 100 by 100 in dimension is one thing, and implementing it on an actual physical device is another thing. Yeah, I mean, will the poor person who will be designing the computer have to build a special hardware for my new 100 matrix. Okay? If you already have elementary operations, for instance, in classical computation, we have the AND gate, OR gate, NOT gate, things like that. Those are called elementary operations that can be done easily on like 2 or 1 bits. Then every other program that you can imagine can be written, can be broken down into sequences of those elementary gates. Something like that is valid for Adamar and CNAT in the world of quantum computation. That's why this combination. There are some other sets of elementary gates, but these are the easiest ones to talk about. Are we okay? Okay. So, given 2 qubits, originally at both of them at 0. Maybe you can do this as an exercise, right? By applying Adamar to one of them, and then CNAT to both of them, using one of them as the control and the other one as the target. Right? By doing like just a very small number of elementary operations on this, you can convert it to that thing. Okay? By making those few quantum steps on it, you can convert your 2-qubit system to be in that interesting state. This state is what Albert Einstein didn't like. Because, you know, Einstein was, of course, he was also one of the main contributors to quantum mechanics. He made some of the discoveries that make up the entire thing. And in fact, in his attempts to disagree with the other guys who invented quantum mechanics, he also made some more discoveries. Right? I mean, the fact that he said, I don't like this, actually teaches us a lot of things about the interesting features of quantum mechanics. Okay, why did Einstein not like this? Let us examine. So, are we all cool? When we observe this, we will observe 0, 0 and 1, 1 with equal probability. But Einstein said, what if? Okay, after all, these are like 2 quantum bits, 2 different separate quantum systems, right? I'm calling it Q00 because I'm observing it as a single, I'm imagining it as a single system, all right? But he said, what if, after obtaining this state, we carried one of the qubits away to a very distant place, right? Light years away from the camera, so now I'm not on the camera. Really considerably far away, all right? And the other one stayed here, and traditionally one of them is maintained by somebody called Alice, and the other one is maintained by somebody called Bob. Anyway, so, and then Alice observed her bit. What's the probability that Alice will see a 0? 1 over 2, of course, okay? And similarly for 1. Einstein said, well, once Alice has observed a 0, let's say, it is certain that Bob will also observe a 0 when he opens the box. Right? Because, yeah, it's really not possible to have a 0, 1 or 1, 0 in this situation. Similarly, when Alice observes a 1, it is certain that Bob will also observe a 1. Even if he does it like immediately, at the same moment. I don't know if something is even possible to say in relativity theory, but you see what I mean. I mean, without there being enough time for a message to go from Alice to Bob through like space. This is like messaging faster than light, and you know Einstein cannot accept anything going faster than light. All right? That's why he was so annoyed about this. Do you see the problem? But it really is like that. Sorry. All right? But this is actually not against relativity theory. If you note that nothing is going from Alice to Bob, really. No information is going from Alice to Bob. Alice is not sending a message to Bob. In order to send a message, you first have to decide what the message is. I want to send a 0 to Bob today. I don't love you, right? And then press the button, and then we can talk about, you know, how much time it took for the message to travel. All right? But that something like that is not happening. Alice is not controlling what she sees. But the interesting thing is they will see the same thing. Okay? So according to one of those, actually the dominant interpretation of quantum mechanics, people would be forced to interpret it as, yeah, really something, some news that the system has collapsed from its superposition state to 0, is traveling very fast, in fact instantaneously, to the other place, right? And that was bothering Einstein. That also is bothering me, but I think that interpretation is the wrong interpretation anyway. One of the alternative interpretations of quantum mechanics, of things like that, as I mentioned, is the parallel worlds, multiple worlds interpretation. And in that case, when you are doing this, when you are converting 0, 0 to this using your Hadamard and CNOT gates, actually the Hadamard gates does the splitting, right? From that moment on, there are two universes. All right? The universe where it's 0, 0, and everything else in the universe is the same. I mean, the two universes disagree only on the contents of these two qubits. All right? And an equally weighted universe where that part of the universe is 1, 1, and all the rest of the universe is the same, including copies of you, me, and everything. Right? And then in both universes, one qubit goes. It has to be isolated really well because those things only happen when you are isolated from the rest of the universe, right? To that distant location. And all the time in universe number 1, they are both 0. In universe number 2, they are both 1. All right? So now it is not surprising at all that Alice opens up a 0, and of course Bob also will see a 0, and so on, because that was the 0, 0 universe all along. When you interpret it according to that, it's okay. People who don't like the multiple worlds interpretation say that in science you should pick the smallest explanation for things, right? If there are alternative explanations for explaining the same thing, whichever one involves like the smallest amount of words, smallest amount of information or whatever, it seems should be chosen if you don't have any experimental evidence against it, right? And they say that, well, the multiple words interpretation is not small at all because it involves like 10 to the something universes splitting all the time. That's just the opposite of small, right? But anyway, that's a long story. What matters is that, I mean, I should stress this again and again, there are disagreements among physicists about how to interpret those things, but the mathematical stuff that we are writing on the board are agreed on completely by everybody and validated by experiment again and again. So it really works like that. Okay? Really, systems have states like this, and transformations are unitary matrices like that. These sorts of matrices are called unitary matrices. And everything works according to those principles. So we can build computers according to those principles. Are we okay? Okay. So, technically, the relationship between these two qubits, once we have done them, once we have put them into that sort of situation, is called entanglement. You may have heard about it. Dolanıklık in Turkish. It's a very good word, I think. They are entangled, right? If one is something, the other one just has to be something associated with that thing. Which is something really that we don't have in the classical world. All right. Okay. Now that we have talked about our elementary gates, Adamar and Sina, there are others, because there are obviously infinitely many really matrices that you can apply. Real numbers, there are so many real numbers, right? And but thinking of quantum operations in terms of those two elementary ones, or like a few elementary ones, sets, makes thinking a lot easier. Then the job of the quantum engineer is just to find the appropriate sequence of elementary gates to apply one after another to obtain the effect of this big transformation that you have in mind. All right. So the idea of entanglement, I mean, Alice and Bob, far away from each other, are sharing something in this mysterious way, something which agrees, right? In this mysterious way, has been used for wonderful cryptographic protocols, where really this Alice and Bob terminology comes from cryptography anyway, right? Two people want to communicate, and other people may want to listen in, but we want to be so clever so that only the people who are communicating can understand what each other is saying, and anybody who listens cannot. So by making a few more additions to this basic idea, you really can obtain provably secure communication protocols, in the sense that, you know, somebody who tries to listen, for instance, captures the qubit while it is traveling from Alice to Bob and measures it and so on, and then prepares a similar qubit and sends it to Bob, right? We can prove theorems that such a person cannot be really successful in listening to those people without herself being detected. All right? Which is very, very good. It's like the sort of the end of thousands of years of thinking about how we can communicate securely, and it is already in practice. Quantum cryptography, those protocols related to sending qubits securely are already implemented nowadays by actual people. Cryptography is like much more advanced than computation. You may have heard that like the biggest, best quantum computer in the world is only able to deal with like 50 or 60 qubits. Quantum computation is more difficult than quantum cryptography because of the following reasons. Well, as you saw, in quantum cryptography, it's okay if you are sending only like single qubits, a stream of single qubits, one qubit and then another qubit and then another qubit and so on. And it's so much easier to isolate for sufficient amounts of time a single qubit from the rest of the universe, corresponding to what you have to do in quantum computation. In a computational system, let's say you have, I don't know, if you are trying to do something meaningful, you must have, I think, a few thousand bits, a few thousand qubits, right? And they have to be isolated from the rest of the universe. Difficult. And they have to be like non-isolated from each other because they have to work together, right? So ensuring both these things, I think, I'm not a hardware guy, is difficult, right? Drawing the box around them so that they don't interact until you want them to interact with the rest of the world. And they do interact with each other in the way that you want them to interact. They like obey those matrices. Those are implemented by ingenious physical devices built by clever people, depending on the actual implementation of qubit that you have. As I told you, it really doesn't matter exactly which detail you are using to implement them. I talked about the hydrogen atom, but there are many, many, many other ways of implementing qubits. Electrons have got some strange property called spin, which may be either this or that, so it's good for implementing bits. And there are many, many, many other ways. I mean, as long as there are things that can be different, things that can be more than one state in the world, quantum theory says that it can be used as a qubit. It can be that state with amplitude this and that state with amplitude 1 minus whatever. All right? So, in order to demonstrate at least a little idea about how quantum computation is different than classical computation, maybe we can use Adamar again. So, what happens if you throw two coins? No, one coin twice. One classical coin twice. Okay? Did you throw one classical coin twice? Did you throw it once? So like coin thrown once is this, right? 1 over 2, 1 over 2, 1 over 2, 1 over 2. Correct? If it's originally in this state, after throwing it, it will be in this state. 1 over 2, 1 over 2. As everybody would expect. Alright? If I throw it again, what will happen? If you see what I mean, what do I mean by throwing it again? I mean by doing that thing to it again, without actually looking whether it was 0 or 1. Alright? So, I mean, I strongly feel that it would be this again. Right? Does the mathematics work out? Yeah, okay. Again, 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 again. And finally, okay, of course, if it's a fair coin, 0 with probability 1 over 2, 1 with probability 1 over 2. Alright? So let's see what Adamar thrown again and again would do to a qubit. Okay? Did we already throw it once? Yes. So if I throw it once, it gives me, from state 0, it gives me 1 over root 2, 1 over root 2, right? Are we okay? And if I apply another Adamar to my qubit in this state, what will it do? So should I do it? Let me see what it's doing. 1. Okay, something different is happening, which we expected because the matrices are not exactly the same. There is this minus there, which is the responsible for everything. All right, but let us try to use this example in order to understand the essential difference between quantum computation and classical computation. All right? Maybe we should draw one of those trees. In the classical world, yeah. Originally it was 0, right? Then the act of throwing sort of divides it into two parallel universes. I mean, in the classical world also you can talk about parallel universes, right? I mean, let me throw a coin, and as a result of that, I don't know, I go to the cinema or I go to the theater, right? So now history has branched into two alternative worlds. In the cinema, I meet somebody, I fall in love, and so on. In the theater, I get kidnapped by somebody. Right? You see? And in fact, if you throw more coins, really you can produce 2 to the big number of alternative universes. Alternative universes is not an impossible thing to do even in the classical world, if you see what I mean. But in the quantum world, it's sort of more real. Let us see how. So, this is the classical situation. Coin throw, So, probabilities of seeing 0 at the end, I mean, these probabilities, right, are what? By multiplying the probabilities along those branches, you obtain 1 over 4, right? 1 over 4 here, 1 over 4 here, so sum them up, 1 over 2, probability of 0. Similarly, 1 over 2, probability of 1. Okay, what happens in the world of quantum? Would you like to consider what's going on in those branches? So I begin in quantum state 0 with 1 over root 2 amplitude something is happening, and with 1 over root 2 amplitude something else. Okay, because it's 1 over root 2, 0, 1 over root 2, 1, right? So in this notation, I started from this and obtained 1 over root 2, 0, 1 over root 2, 1. Okay? And then what? What does Adamar do to this vector? The nice thing about writing it like this is that you can apply them separately to both sides of the addition sign, and then you can pull up the terms together. Alright? So everybody knows that Adamar applied to 0 gives me equals 0 and 1. But this thing had a 1 over root 2 in the front, so I will, okay. So this will give me, just like from this 0, I will get, if you agree with me, 1 over root 2, 0, and 1 over root 2, 1. So really, something like that. And from this 1, if you remember Adamar's matrix, I will obtain what? Once again, 0 and 1, but the 1 will have a minus in front. Right? 1 over root 2, 0, minus 1 over root 2, 1. So really, what's going on here? I can do some algebraic cleaning up. This is equal to 1, really no need to write 1. This is equal to this, because the 1 qubits values have cancelled each other out. Over here, if you interpret these things as parallel worlds, something interesting happened. So in the world of parallel worlds, right? Over here I was in 2 parallel worlds. 0 and 1. Now one step later, after the second Adamar operation, I am back in 1 parallel world. I am back in 1 world. Right? What happened to those other parallel worlds? Well, because of those amplitudes, you know, why did we talk about waves? Those people have a reason for talking about waves. It really is like waves. You know, when there are like 2 waves, you throw 2 stones, one here and their wave patterns are interfering with each other. In locations where like the first wave is doing this and the second wave is doing that, they cancel each other, and that part of the water is like still. Right? That's what's going on here. Those 2 worlds, or like, yeah, really, those 2 worlds cancelled each other because they were describing the same thing, but their amplitudes were exactly opposite to each other. That's gone now. Right? No such possibility remains now. Okay? In general, quantum algorithms, really all quantum algorithms that I know, especially like the very famous ones like Shor's algorithm and so on, I think you will see Grover, that's all. Really anything which uses a minus, and without the minus you are not really a quantum algorithm, is making use of this idea. You have your initial state. You are a clever person who wants to solve a solution. At the end, you want your computer to show you the solution when you look at the qubits finally. Right? And generally, the quantum algorithm ideas, there are not so many alternative quantum programming ideas. It's a very, very difficult thing to think of new quantum programming ideas. Shor was considered for a Nobel Physics Prize this year. I read it in some physics journals immediately before the Nobel Prize announcements. Anyway, so like, good ideas are very rare. Anyway, generally quantum algorithms do this, right? They start evolving your system through those parallel worlds. They are trying to attempt to find something which looks like a solution. So in many, many parallel worlds, if you have 100 bits in 2 to the 100 parallel worlds, stuff is happening. But only in some of them you have hit upon the correct solution. All the others are wrong solutions. And clever algorithms, cleverly, the details are of course important, are able to make the wrong solutions cancel each other out, so that at the end, when you observe the computer, you see the correct solution with high